In this video, we're going to be talking about a reaction known as the autoionization of water. So this reaction is happening at all times in all aqueous solutions. So even if there is some other reaction going on, no matter what it is, even if there is no other reaction going on, if you have water, you have this reaction happening. You have this equilibrium that has been established. So the autoionization of water, if we think about just what the word autoionization means, we know what ionization is, the formation of ions, and the prefix auto refers to doing something to yourself. So autoionization is water reacting with itself to form ions. We have seen that water is capable of acting as both an acid and a base. It can be either. This property is referred to as being amphoteric or amphiprotic. For our purposes, those words mean the same thing. In some situations, they're slightly different, but for us, they mean the same thing. So amphoteric or amphiprotic. Amphoteric is the more commonly used term. So water can act as both an acid and a base. And in the autoionization reaction, it is doing just that. It is being both at once with itself. You have two water molecules reacting together. One of them gains a proton, thereby acting as a base. The other one gives up a proton, thereby acting as an acid. So when water gains a proton, it becomes hydronium. When water loses a proton, it becomes hydroxide. So this is the autoionization reaction. I should indicate this with double arrows. This is very much a reversible process. So in any aqueous system that you have, this reaction is at equilibrium. It establishes equilibrium very quickly. So if you have a solution just chilling, just hanging out, this is at equilibrium. And we describe this with an equilibrium expression. Just like any other, it is products over reactants, ignoring liquids and solids. Our only reactant is a liquid. Both of our products are aqueous. So this is our equilibrium expression for this reaction. And we labeled this K, Kw. So Kw is just the equilibrium constant for the autoionization of water. So what this allows us to do, or what this allows us to recognize, is that all aqueous systems contain both hydronium and hydroxide, and the product of those two concentrations is equal to a constant. So if we know the value of Kw, and we know one of these two concentrations, we can figure out the other one. So we will most commonly work at 25 degrees Celsius. At 25 degrees Celsius, Kw is equal to 1.00 times 10 to the negative 14th. So it is very small, meaning that this is a very reactant-favored reaction. Not a whole lot of hydronium and hydroxide are forming, but a little bit. And the product of those two concentrations is always equal to Kw. which as long as we're at room temperature is 1 times 10 to the minus 14th. So if we take this in conjunction with the equations we talked about last time, that we have pH is equal to the negative log of the hydronium concentration, or hydronium is 10 to the minus pH. OH is negative log of hydroxide, or hydroxide is 10 to the minus POH. If we now throw this equilibrium expression into the mix, that Kw is equal to hydronium times hydroxide, this expression kind of acts as a bridge between these two different sides of things. That if we know the pH of a solution, we can find the hydronium concentration. If we know the hydroxide concentration, if we know the hydronium concentration, we can find the hydroxide concentration. And once we know the hydroxide concentration, we can find the POH. So if we know any one of these quantities, we can find all of the other ones using this relationship. So let's give that a try. So if we have, we'll say we are at 25 degrees Celsius here, which means that this is our value for Kw that we can use. If we have a hydronium ion concentration of 6.5 times 10 to the negative 4th molar, I would like you to take a moment and, exactly like we did last time, calculate the pH. Then, using this new expression that we just found for the autoionization of water, calculate the hydroxide ion concentration. Once you have the hydroxide concentration, you can calculate the POH. So take a couple minutes and try to do that now. So calculating our pH is pretty straightforward here. We will do the negative log of the hydronium concentration, which is 6.5 times 10 to the minus 4th. So we get a value for pH of 3.19. So that exactly like we did last time. So if we want to calculate our hydroxide concentration, we're going to need to use this. So if we rearrange this relationship to solve for hydroxide, which is what we're looking for here, we'll need to divide both sides by hydronium in order to do that. So we'll get that the hydroxide ion concentration is equal to Kw divided by hydronium. So if we take that with the numbers that we actually have, we're told at 25 degrees Celsius, which means this is our value for Kw. So we'll have 1.00 times 10 to the minus 14th over our hydronium concentration, which was 6.5 times 10 to the minus 4th. So that gets us a hydroxide ion concentration of 1.5 times 10 to the negative 11th molar. And from there, if we want to calculate our POH, we just need to take the negative log of that value, which is 10.81. So once we know just one of these quantities, so we started out with just the hydronium concentration given, we can figure out everything else. Since we now know how hydronium and hydroxide are related in solution, which is through the autoionization of water, that tells us the product based on its equilibrium expression, the product of the hydronium and hydroxide concentrations is always equal to the value of the equilibrium constant for autoionization. If we're at 25 degrees Celsius, this is our value. If we're at a different temperature, as we know, K changes with temperature, so that is going to affect the value of K, but that would be given to you and you just need to recognize to use the correct value. There's also another way that we can link between the pH and pOH scales that is still rooted in KW and in the autoionization of water, but can sometimes be a little bit simpler to work with depending upon what numbers you have. So we know that pH is the negative log of the hydronium concentration. And we know that pOH is the negative log of the hydroxide concentration. So this little p here is really a function. P whatever means take the negative log of that thing. So pH is the negative log of the hydrogen concentration. pOH is negative log of the hydroxide concentration. So if we think about this equilibrium expression that we wrote for autoionization, it has hydronium, it has hydroxide, which are related to pH and pOH respectively in the same way, that they're both negative log relationship. So let's imagine what would happen if we took the negative log of both sides. So if we have the negative log of KW and we take the negative log of the hydronium concentration times the hydroxide concentration, by the laws of logarithms, this is the negative log of hydronium plus the negative log of hydroxide. So right here, we have the negative log of hydronium is our pH. We have the negative log of hydroxide is our pOH. And this equation is telling us that the sum of those two things is equal to the negative log of KW, which we call pKW. So if we know KW, we can find pKW just by taking the negative log. So let's say at 25 degrees Celsius, if the pH of a solution is 2, what is the pOH? So to solve this, we could absolutely go through the whole process that we did before, where we go from pH to hydronium, and then we can go from hydronium to hydroxide, and then we can go from hydroxide to pOH. But this relationship allows us to go directly from pH to pOH. So depending on what information you have and what information you're solving for, one route or the other may be faster. So all we need to do here really is recognize that at 25 degrees Celsius, KW is 1 times 10 to the minus 14th. So pKW is the negative log of 1 times 10 to the minus 14th, which is equal to 14. So at 25 degrees Celsius, the pH plus the pOH is going to be equal to 14. Again, if the temperature changes, KW changes. If KW changes, pKW changes. But most of the time we'll be at 14. So we were given a pH value of 2 And this is really easy now to solve for the POH, which would be 12.